Okay, this next section out of the structure of atoms and periodic trends will be atomic properties and periodic trends. So let's go ahead and get to it. So atomic properties and periodic trends. The goal is to predict how properties of atoms, size, ionization energy, which is abbreviated uppercase I, uppercase E, and electron attachment enthalpy, which is abbreviated as delta EAH, vary within a group and across a period of the periodic table. So it's important to remember that periods are these horizontal rows and groups are these vertical columns on a periodic table. So we want to know how these vary, and we want to know the reason why. So let's take a look first at some of these atomic properties and periodic trends. First, we're going to look at atomic size and ionization energy, and then there will be two more. So atomic size, we're simply looking at the radius of the atom. Ionization energy is the energy required to remove the least stable electron from a gaseous state atom in its ground state. So all the electrons are in the most stable configuration. We're calculating or determining the amount of energy to remove the easiest electron to remove. So if we take a look at lithium as a gaseous atom, when you remove an electron, it becomes a lithium cation, and here's the electron removed. And so this energy is the change in internal energy, which is the ionization energy. This is an endothermic process, so it's something where you have to add energy, and the change in energy is positive. So if we look at the SPDF notation of lithium, it's 1s2, 2s1, and we're looking at taking away this 2s electron because it's the least stable. So this lithium atom becomes 1s2 and a lithium ion. And here's the electron that's been removed. If we look at the noble or the orbital gas notation, orbital box notation, we have two electrons in the 1s, and here this should say 2s, one electron in the 2s, and you take away this electron that's the easiest to take away. Okay. The other two periodic trends we're going to look at are electron affinity and electron attachment enthalpy. This is really one trend. These two are opposites of one another. So let's look at electron attachment enthalpy, this delta EAH. This is the amount of energy change when you gain a gaseous electron. So here we have a gaseous fluorine atom getting a gaseous electron, and it becomes a fluoride ion. The energy change here is called delta or electron attachment enthalpy, delta EAH. Now this is exothermic. This is something that releases energy, so it's a negative value. So when we start talking about what's bigger and what's smaller, it can get confusing because these have negative signs. But if you just remember the amount of energy here is being released because it's exothermic, you can still talk about which one's more exothermic. And you could say, if you wanted to look at the sign, you could say which one's more negative, okay? Electron affinity is the opposite of this electron attachment enthalpy. So here you're just dealing with positive values. So it's really easy to look at electron affinity and say, hey, you know, which one has more electron affinity? It's the one with the larger positive value. So it's just a way to try to talk about these where you don't worry about the negative sign. And we're also going to look at ion radii. So let's look at the trends for all of these. So here I've got the period trend, which means the horizontal trend in a period, and I've got the group trend, which means the vertical trend in a period. So, or I should say not in a period, a vertical trend on the periodic table. So here's the deal. For atomic radii, as Z effective increases, the radius increases. So this is interesting. When you go across a period, and you start on the left and go to the right, that's Z effective increases. Remember, we talked about this before. You look at lithium over to fluorine, Z effective or Z star increases when you go from lithium to fluorine because you have more protons in the nucleus. It turns out that fluorine is smaller than lithium. Wow, that's kind of amazing when you think it's got more protons and it's smaller. Okay, so that's a periodic trend. And let's see if the book actually shows us a little chart. I hope it does. And maybe we can see that. So let's take a look just at atom radii, just so that you can believe me here. So we're going from left to right. Look at the size when we go across. They get smaller and smaller. They get smaller and smaller. There are some things where it reverses a little bit in here, but for the most part, they get smaller and smaller from left to right. When we get into these elements down here on the lower part of the periodic table, it works kind of okay, but there are some reversals here. Now, what about the group trend? As Z star increases, the radii increases. So let's take a look here. As Z star increases, as the effective nuclear charge increases, which means you have more protons in the nucleus, the radius increases. So take a look here, going down. As we go down, you get more protons in the nucleus and the size increases. So you can see that that is the case regardless of whatever column you're in. It gets bigger as you go down the periodic table. Okay, so that's the atom radii. Then there's the ion radii. So here, if we look at the ion radii, so this is this is atomic radii. Let's see if we can find ion radii. Okay, here's ion radii. Now, I'll be honest with you. For this, you have to compare apples to apples and oranges to oranges. And so what that means is when you compare an ion radii, you're going to compare cations to cations and anions to anions. So let's look across the group at what happens to the anion size, which is over here. And the answer is the anion size decreases when you go across to the right. The anion size decreases almost in every case, actually in every case that we see here. Let's look at the cation size. What happens? Well, here also in every case, the cation size increases from left to right. Now, what happens for the cation size when we go from top to bottom? The bottom ones are larger. So that's just like ion radius or atom radius. And here's the same thing. They get bigger and bigger and bigger. So we want to be able to understand that trend and figure out, well, why? We'll get into that a little later. Now, for ionization energy, as Z star increases, it's harder to take away an electron. And that kind of makes sense, right? I mean, the more protons you have in the nucleus, the harder it is to take an electron away from that nucleus. And here, that's in a period. In a group, when you get to a larger nucleus, Z star, the electron affinity becomes smaller. Now, that's kind of interesting. And we want to know why. Now, for electron affinity, remember, this is the opposite of electron enthalpy energy. Here, when Z star increases, the affinity increases. And for the group trend, it turns out there's no real trend. And we do have images of that. Here is the electron attachment enthalpy. So you can see that in general, in a period, it gets larger and larger, but there are some weird things going on there where it goes up and down. And when you look at the group trend, you can see here, this group trend, it decreases. This group trend, it stays flat the whole time. This group trend, it goes up and down, up and down. Here, this one goes up, up, up. This one goes up and then slightly down, and this one goes up and down. There is no real group trend there. And if we go back to ionization energy, which is right here, you can see when we go from left to right, it generally increases, and when we go down, it decreases. Okay, so we want to understand why these trends are the way they are. So I'm going to discuss that. I'm going to show you that in some of these cases. So let's take a look at atom size and ion size and why the trends are the way they are. So what I have here is we have lithium and hydrogen. So we're looking at a group now. Lithium and hydrogen are in the same group, group 1A. Now, lithium is larger than hydrogen. Now, why is that? And the answer is, look at the electron configurations. The explanation for all of these is look at the electron configuration. And the best thing to look at is probably the orbital box notation, although you don't always need to do that. So here, why is lithium bigger than hydrogen? And the answer is, it's got electrons in a larger shell. So a larger numbered shell usually means a larger atom. What if the shells are the same? Well, then you have to look at that in more detail. So here, a lithium will be bigger than a hydrogen because we're talking about a larger outermost occupied shell. So how about fluorine and oxygen? Fluorine is actually smaller than oxygen, which is interesting because fluorine has more electrons. So why is fluorine smaller than oxygen? And it turns out that Z effective for fluorine is greater than oxygen, and they're both pulling these electrons in from the second shell, and they're pulling them in with their protons. Who's going to be able to pull those second shell electrons in better? Fluorine with its 9 protons or oxygen with its 8? And the answer is fluorine. And that's why fluorine is smaller, because it is pulling on the same outermost shell electrons, the second, and it has more more protons to pull those electrons in. So that's the explanation for the trends in the groups and the periods. And you can see that what we're looking at is two things, two factors. One factor is, what is the outermost occupied shell? Because if the outermost occupied shell is different, that's going to be your explanation. And if the outermost occupied shell is the same, what's your explanation? It's going to be the number of protons in the nucleus, or the Z star, Z effective. And so the same thing goes for ion size. If we look at F minus versus O2 minus, which one's smaller? It turns out that the fluoride ion is smaller. These both have 10 electrons. Fluorine has 9 protons, oxygen has 8. Who's going to pull in 10 electrons better? Fluorine with 9 protons or oxygen with 8? Well, fluorine with 9. So that's why fluorine is smaller. It has a larger effective nuclear charge, pulling the electrons in better, making it smaller. Now, what about fluoride versus chloride? So this is a group trend. And well, chloride's going to be bigger than fluoride because fluoride only has this 2p6, where chloride has a 3p6. So larger outermost occupied shell. Now, for ion size, we do have to remember this. For ion size, we've got to look at cation versus anion, and we're going to look in a period. So if we go back to that image that shows you pictures of or cartoons of cations versus anions in the same period, let's take a quick look at that. Can you see here that the cations are always smaller than the anions? So let's just take a look at these two here, this aluminum cation and this sulfide anion. So here, the cation in a period is going to be smaller than the anion. And in fact, it's going to be much smaller. So when you put two of those arrows, it means a whole lot smaller. So when we look at the aluminum cation, it's going to be a 1s2, 2s2, 2p6. And aluminum is atomic number 13. And when you have a 3+ charge, you're going to have 3 electrons less than 13 or 10. So this is what aluminum plus 3 looks like. And if you look at sulfide anion in the same period, it's 1s2, 2s2, 2p6, 3s2, 3p6. So look at these. Why is the aluminum so much smaller than the sulfide? And the answer is because it only has electrons in the second shell in the ground state, and sulfide has electrons in the third shell in the ground state. That different shell makes all the difference in the world. So this guy's going to be a whole lot bigger than that because it's got a larger outermost occupied shell. Okay, so that's what's going on with the cation versus the anion. And what about cation versus cation in a period? So it turns out that if we take a look at magnesium, magnesium with a +2 charge is greater than aluminum with a +3. So why is that the case? Well, if we take a look at magnesium, it's 1s2, 2s2, 2p6. And if we look at aluminum +3, it's 1s2, 2s2, 2p6. So why is magnesium bigger? Well, it turns out that magnesium has 12 protons. Aluminum has 13 protons. They both have 10 electrons. So who's going to suck those electrons in better and make you a smaller size? Aluminum. Okay, so remember, when we're looking at these trends, there's basically two things you're looking at. You're looking at, do they have the same outermost occupied shell? If not, that's the explanation for the difference. And if they do have the same outermost occupied shell, 2p6, 2p6 here, then what's going to be the explanation for the difference? Usually it's the number of protons in the nucleus. Okay, let's take a look at explanations for trends. You can see that I've written that usually if you have a different n, that's going to explain the difference. Same outermost n, it usually depends on Z star. And then sometimes it's going to be paired versus unpaired. So I'm going to have to give you an example of where paired versus unpaired explains the difference. But let's see if we have a problem that we want to look at. So here's the periodic trends, but I do want to take a look at a problem that's not here. So I'm going to write it down. So here's the question I'm going to pose to you. And it's simply this. In general, as Z star increases in a period, electron affinity, straighten this out, electron affinity also increases. Okay, so that's the general trend. However, the electron affinity of, actually, I don't want to do this for electron affinity because electron affinity is really goofy. So we're going to cross this off and we're going to rewrite this problem. And we're going to write it for ionization energy. So in a period, as Z star increases, ionization energy also increases. And this is generally, not always, but generally. So remember, when we talk about ionization energy, it's the energy required to remove an electron. So if we take a look at, say, boron and carbon, this is definitely the case. So the ionization energy of boron is smaller than the ionization energy of carbon. And on the periodic table, they look like this: boron, carbon, nitrogen, oxygen, fluorine. So here it increases. So when we go across, ionization energy increases. So we expect carbon to be greater than boron. And there it is. So why is this the case? Well, when you look at boron, boron is 1s2, 2s2, and 2p1. So that's boron. If you look at carbon, it's 1s2, 2s2, and 2p2. So these are the electron configurations using the noble gas notation or the orbital box notation. And this electron is easier to take than this one. So why is that? Well, the answer is because boron has 5 protons and carbon has 6 protons. So Z star is going to be greater for carbon. So when you look at this guy versus this guy's going to be harder to take because they're both coming from a 2p, but this has a greater effective nuclear charge. Now, this is weird. If you look at the chart, it says that the ionization energy of nitrogen is not less than oxygen, it's greater than oxygen. So this bucks the trend. So why is that the case? Well, let's take a look at nitrogen versus carbon. So nitrogen is 1s2, 2s2, and 3s, or 3p, I'm sorry, 2p, not 3p. What am I thinking? Nitrogen is going to be 1, 2, 3. Oxygen is going to be 1s2, 2s2, and it's going to be 2p4. So which electron are we going to take out of each of these? And the answer is you're going to take that one. I always say the last one in is the first one out. Last one in is the first one out. So here, this is the one you're going to take. You're going to take a unpaired 2p. Which one are you going to take out of the oxygen? And the answer is this one. Last one in, first one out. This one is a paired 2p. Now, why would you take this one instead of one of these singles? And the answer is these two electrons repel one another. So putting another electron into an orbital, while it's okay, it's not ideal because the electrons repel one another. That's why we have Hund's rule where you put electrons into orbitals singly before pairing them, because pairing them is an energy cost. So here you got to think about this electron here that we're taking out is already kind of being given the shove from the other electrons, like, hey, just leave. So that means that this pair 2p is easier to take. So the ionization energy is less. So the general trend is to go bigger when you go to the right, but there are these little Buxton trends. So here, how can we tell that this is a paired versus an unpaired? And the answer is you got to go with the orbital box diagram to see that. So if you write out the orbital box diagram, first thing you want to do, if you're looking at the orbital box diagram, to see if there's a reason for the particular trend, once you write out the orbital box, you look at outermost occupied shell. If they're different, that's going to be the reason for the trend. But you don't say, hey, it's just because they have an outermost occupied shell. You say, well, hey, this electron is farther from the nucleus, it's easier to take. Next thing you look at is you look at Z star for the same outermost occupied shell. So this is going to be your reason, your outermost occupied shell, if they're different. But what if they're the same? Well, then you're going to look at Z star. Well, what if Z star doesn't seem to explain it? Then what do you look at? You look at paired versus unpaired. And if you go down that list one by one, and if the first one doesn't explain it and the second one doesn't explain it, it's probably going to end up being paired versus unpaired. So that's how you explain these trends. So let's take a look here at some problems. So, periodic trends. Compare the three elements, carbon, oxygen, and silicon. Place them in order of increasing atomic radius. So if I draw just a periodic table where we see carbon, oxygen, and silicon, there's carbon, there's nitrogen, and there's oxygen, and here's silicon. So if I look at silicon versus carbon, silicon is definitely bigger than carbon because silicon is lower on the periodic table, so its outermost electron is larger. So if we take a look at the electron configurations of each of these, which will help us to understand this, we'll look at carbon, which is 1s2, 2s2, 2p1, excuse me, 2p2, there's carbon. Oxygen is 1s2, 2s2, and 2p4. And silicon is going to be, since it's in the next period, it's going to be neon, 3s2, 3p2. So these are the electron configurations of each of these. And the atomic number for each of these is 6, 8, and for silicon, I can't remember what it is. I want to say like 14. Oh, and it is 14. So when we go down the list of reasons for what is what, we want to take a look here at carbon versus silicon. You see that the outermost occupied shell is a 3p for silicon, and it's a 2p for carbon. So that's why silicon is larger than carbon. Now here, we don't want to compare silicon to oxygen because they're not in the same group and they're not in the same period. But we can compare carbon to oxygen. So let's take a look at carbon and oxygen. Now, the outermost occupied shell is the 2p, or subshell is the 2p. They're the same, so we can't use that as a reason for why they're different. So what do we go to next? We look at the charge here of the nucleus. +8 pulls the electrons in better than a +6. So that means that carbon is going to be larger than oxygen because oxygen has more protons in the nucleus. Okay, let's see. Can we put these together into a nice order? Well, clearly oxygen is smaller than carbon. So here, this says in order of increasing atomic radius. So I would say that oxygen is smaller than carbon. So we're going from left to right, increasing. And then carbon, you can see, is smaller than silicon. So here's the order. And we could use the electron configurations to figure that out. Okay. We can probably do the same for B, which has the largest ionization energy. So this is the amount of energy required to remove the electron. So I've got to say that silicon is the easiest because you're taking a what looks like a 3p electron. Now, what's going to be easier for oxygen or carbon? Now, this does look like we're taking a paired electron. And this does look like we're taking an unpaired electron, but that's the third reason why you look at things, right? The second reason here is you're looking at effective nuclear charge. Oxygen's effective nuclear charge is much greater than carbon. A difference of 2 is a significant difference. So here, what we would say is, well, if oxygen is an 8 and carbon's 6, it's going to be easier to take it from carbon than from oxygen. So oxygen harder because the Z star is +2 over carbon. If it were only +1, then we'd have to say, oh, maybe we better look at the paired versus unpaired. Okay, so here, when we're looking at electron affinity, ionization energy, which one's going to be the easiest? Silicon, then carbon, then oxygen. Now, what is C? Which has the more negative electron attachment enthalpy? So this really is which one has the more positive electron affinity. So for C, for electron affinity, which one's going to have a greater affinity for electrons? Well, let's take a look here. If you look at silicon, it doesn't have a great affinity for electrons because you're only going to pull the electron into the 3p. So silicon's definitely going to be the smallest. And then when you look at carbon versus oxygen, you've got to ask yourself, well, which one has a larger effective nuclear charge? Oxygen does, so it has more affinity for the electron. So you're going to put carbon and you're going to put oxygen. You can see that this trend is very similar to this trend and opposite to this trend. Okay, so that's how you go about trying to explain these things. All right, let's take a look at another one. Okay, arrange the following elements in order of increasing size: aluminum, boron, carbon, potassium, and sodium. So for that, we're going to have to draw the periodic table again. Here's aluminum. Boron is right above it. Carbon is right next to it. And if we look at the periodic table, sodium is in the same period as aluminum, and potassium is down here. Okay, so here I'm going to write out the electron configurations of each of these. So boron is 1s2, 2s1, carb or 2s2, 2p1. Carbon is 1s2, 2s2, 2p2. Sodium is 1s2, 2s2, 2p6, 3s1. Aluminum is 1s2, 2s2, 2p6, 3s3 is what I want to say. Yep. And potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, or excuse me, 4s1. So we want to put these in order of increasing size. So I can tell right away just by this electron configuration, because we have stuff in the fourth shell. Potassium's the biggest. So I'm going to put that way over here. That's the biggest. Now, which of these is going to be the smallest? Is it going to be boron or carbon? Because they only have things in the second shell. And the answer is, well, here boron has 5 protons, carbon 6, sodium 11, aluminum 13, and potassium has 21, I think. Oh no, 19. So here, these guys are in the same period. And remember, the one with more protons will be smaller. So between these two, carbon's going to be smaller than boron. Now, how do sodium and aluminum fit into all of this? Well, if we take a look, clearly they're going to be smaller than potassium because there are only third shell electrons here. So which of these two are going to be smaller? And remember, in a period going from left to right, they get smaller. So that means that we expect aluminum to be smaller than sodium because it's got 13 protons sucking in those third shell electrons better. Why do I have this as 3s2? This should be 3p1. Bad Tony. Okay, so this is the increasing size. So we want to have small size to the left and large size to the right. Next we have select the atom or ion in each pair that has the larger radius. Now, we haven't really looked at this, but for chlorine versus chloride, chlorine is going to be a neon, 3s2, 3p5, and chloride's going to be neon, 3s2, 3p6. So here we have to decide which is going to be larger. Chlorine and chloride both have 17 protons. So which one is going to pull in these third shell electrons better? Neither, because they both have 17 protons. As far as the size goes, they're both 3s. And so this is like the fourth thing that you want to compare. How many electrons do you have in that outermost shell? So here, 3p6 versus 3p5, you expect the chloride to be larger than the chlorine. Aluminum or oxygen, you expect aluminum to be greater than oxygen. They're not even in the same period. Indium or iodine, if we take a look, indium and iodine, they're in the same period. So we would expect iodine to be smaller than indium because iodine has more protons in its nucleus. That's what we would expect. Okay, and lastly we have here, which of the following groups is arranged correctly in order of increasing ionization energy? So we're talking about difficulty of removing an electron. And remember, if it's a smaller shell, it's harder to remove. So let's take a look at these. This is in the second period, so it only has electrons in the second shell. This is in the third period, so it has electrons in the third shell. So when you take a look at these, it looks like the easiest one out of all of these, to me, looks like it should be silicon, right? Now, which one's going to be the hardest? Well, when we look at neon, lithium, and carbon, they're all in the same period. So which one's going to have be the most difficult to remove from? And that's going to be neon because it has more protons in the nucleus. How about the next? It's going to be carbon. So here I know for certain that neon's got to be greater than carbon. So I like this. And over here, I don't like this because neon's less than carbon. Here I don't like this because neon's less than carbon. Here I do like this because neon is greater than carbon. Now, what about carbon and lithium? Well, carbon's more to the right, so it's going to be harder to take an electron. So carbon should be more than lithium. So here, carbon is less than lithium. So I know I like C. And the thing that surprises me actually is that silicon has a greater ionization energy than lithium. And so we learned something by doing this problem because we know that ionization energy increases when you go across in general. So neon is greater than carbon, carbon is greater than lithium. All right, so there's that one. So let's see. We only have one more page here of problems. So let's take a look at these. Compare the elements: sodium, magnesium, oxygen, and phosphorus. Which has the largest atomic radius? So I'm going to pull out my periodic table here. And I'm going to see if I can find my dry erase pen. And I can't. So here, let's try and find these. We've got sodium here. We've got magnesium here. We've got oxygen up here. And we've got phosphorus here. So which has the largest atomic radius? It's got to be sodium because they get smaller when they go to the right. So the answer to A is sodium. Why is sodium bigger than oxygen? Well, because sodium has something in the third shell. Oxygen only has something in the second shell. And when I say something, I'm talking electron. Which has the most negative electron attachment enthalpy, which is another way of saying which one wants an electron more? Well, I think it's pretty obvious. We know that these guys turn into cations. That means they don't want electrons. These guys turn into anions, which means they want electrons. So it's oxygen. Oxygen has the most negative electron attachment enthalpy. Place the elements in order of increasing ionization energy. So here, increasing difficulty of removing an electron. Well, I got to say, oxygen wants electrons, so removing one's going to be really tough. So this is going to be the most negative, or the hardest to remove an electron. Phosphorus also wants to be a positive charge or a negative charge, so it's going to have a very high electron affinity. And electron affinity generally increases when you go across, so we got to expect that probably it's going to be oxygen first, the biggest, then phosphorus, and then I'm actually going to put sodium before magnesium. I think it's harder to take an electron from magnesium. No, I'm going to reverse that. I think magnesium might actually have a smaller, no, sodium should be smaller than magnesium because it has fewer protons in the nucleus. But on the other hand, from magnesium, you're taking a paired one. So, that's a toss-up on these two. And here's what I mean by that. Let's take a look at magnesium, oxygen, and phosphorus for ionization energy. So sodium, you're looking at a neon, 3s1. Magnesium, you're looking at a neon, 3s2. Phosphorus, you're looking at a neon, 3s2, and a 3p. Let's see, phosphorus is 1, 2, 3, 1, 2, 3. The number of protons is 11 protons, 12 protons, and 14 protons, or 15 protons. And then you have oxygen with 8 protons, and we have helium, 2s2, 2p4. So for ionization energy, let's look at the electron we're taking away from each of these. For oxygen, it's going to be this one. That's a 2p electron. For magnesium, you're going to take this one away. That's a 3s paired. For sodium, it's going to be this one. That's a 3s unpaired. And for this, we're looking at a 3p. So this is a pretty tough one to do now that I look at it in more detail. But let's talk about this in terms of what we do understand. This electron is really close to the nucleus. It is the hardest one to take. Oxygen will have the greatest ionization energy. So now we need to take a look at these other three, and we got to ask ourselves, which one's going to be the easiest to take? In general, since this is a 3, this is a 3, this is a 3, the one that's going to be harder to take is the one that has more protons in the nucleus. So I got to put phosphorus here. Now, what about magnesium and sodium? Well, generally, if you have 12 protons, it's going to be harder to take an electron than from 11 protons. However, this is a paired one. So I got to put a question mark here when I put sodium and magnesium here. I could easily call this for magnesium being easier than sodium. But oftentimes that's not the case when you're talking about s electrons. So you might want to change this and say, well, sodium's going to be easier because it has fewer electrons or fewer protons than magnesium. So you could go with either one of these lists and justify it because you don't know what the actual numbers are. Okay. Last one here. Explain each answer briefly. Place the following elements in order of increasing ionization energy. So fluorine, oxygen, and sulfur. So for fluorine, we're talking about 1s2, 2s2, 2p5 with 9 protons. Oxygen, we're talking about 1s2, 2s2, 2p4 with 8 protons. And here you're taking away a paired. Here you're taking away a paired, and here you're taking away a paired. So paired versus paired doesn't matter. So you got to say that fluorine's going to be harder to take away from because it's got 9 protons. So fluorine is bigger than oxygen. And then for sulfur, sulfur is like 1s2, 2s2, 2p6, 3s2, 3p4. You're taking away an electron from the third shell. So sulfur is definitely the easiest. So this is the easiest. Taking away a third shell electron. Fluorine is the hardest because you're taking away a 2p electron like oxygen, but fluorine has a larger Z effective. So there's your explanation. I'm going to get out another piece of paper here. so that we can take a look at B. Which has the largest ionization energy, oxygen, sulfur, or selenium? So here's oxygen, here's sulfur, and here's selenium. So this is the one where it's harder to take an electron. Here, oxygen has fewer electrons. It's in a different period, so its outermost occupied shell is going to be smaller. So oxygen is 1s2, 2s2, 2p4. You're taking away that electron. Sulfur is neon, 3s2, 3p4. So you're taking a third shell electron. And selenium is argon, 3d10, 4s2, 4p4. So you're taking a fourth shell electron. So this one, oh, I made the mistake here. It should be oxygen, sulfur, and selenium is right below that. So if you take a look at this, which one's going to be the hardest one to take away from? This one, because it's closer to the nucleus. So you got to say oxygen is greater than sulfur is greater than selenium. So this one's a slam dunk. How about C, which has the most negative electron attachment enthalpy? So this means which one wants an electron more? So we've got chlorine, bromine, and selenium. Now, remember, farther to the right, they want an electron more. So also farther up, they want an electron more. So chlorine's going to be the clear winner, then bromine, then selenium. So there's your answer for C. And again, it's because chlorine is going to gain that electron into the third shell. Bromine's going to gain it into the fourth shell. So you give off more energy when it drops into the third shell. Kind of like that lab we did, you know, you drop into the second shell versus the third, you give off more energy when you drop into the second because it's a more stable shell. Okay, so that's it for these problems. Oh, last problem, D. Almost left that off. Which has the largest radius, O2 minus, F minus, or F? Well, if we look at F, it's 1s2, 2s2, 2p5. O2 minus is 1s2, 2s2, 2p6, and F minus is 1s2, 2s2, 2p6. Now, this is tricky because the number of protons in the nucleus is different. This is 8 protons, this is 9 protons, and this is 9 protons. So one thing we can say for sure is when you have the same number of protons, more electrons is bigger. So F minus will definitely be bigger than F. Now, what about this? Well, one thing we can say for sure is if you have the same number of electrons, then smaller number of protons means you're going to be bigger. So when you look at F minus and O2 minus has to be bigger because it has fewer protons. So which is going to have the larger radius? Oxygen. Why? Well, because it's got 10 electrons, which is the most out of all of these, tied with fluoride, but it's only got 8 protons pulling those 10 electrons in. So the oxide ion is going to be the greatest. All right, thank you for listening. And we only have one more subsection to go.